Alright, so in this video over here, we'll be trying to draw derivative functions based on an original function that's given. So over here, we're going to have to follow a few rules over here that will help us out. You don't need to make use of all of these, but if you do use all of them, you can reaffirm that your answer is correct. Okay, so first of all, if you recognize that the original function has a positive gradient, so I'm just going to sketch as we go over here. Now, if I just draw an axis real quick. Okay, it's a bit straighter. Now, if you have some sort of positive gradient, now let's say you got a straight line. And if the gradient is positive, now you can see over here that the gradient is always positive throughout this entire blue line. So in this case over here, you know that our gradient function is actually going to be positive throughout this whole line over here. So if you were to draw f of x, just use a different color. So we have f dash as green. Then it's going to be on top of the x-axis the whole way through. And consequently, the opposite happens for when you have a negative gradient. So if you have a negative gradient, then you're going to have it below x-axis. So just right over here. This implies that negative means that f dash is below. Okay, so this one here I generally regard as optional, and sometimes it may actually give you clues on how to draw a derivative function, or even going backwards from the derivative to the original. So over here, you want to consider the type of derivative. So if f of x is cubic, so if you have x to the power 3, then this means that your f dash would be equal to some sort of quadratic, or in this case, exactly 3x squared. So you can see over here that, especially for polynomials, you can actually just decrease the power by 1 and simply say, well, the derivative should have the shape of this derivative over here, which is a quadratic. Now, that's the case of where the original is a cubic. So you can apply this to actually functions other than polynomials. So when we work with trig functions, you'll find out that, let's say you have a sine function and you want to find a derivative function. The derivative should look like a cosine function. They do look very similar to each other, but it gives you some hints on how you can draw the derivative. Now over here, we have TP and spot. Now TP, just for this video and future ones, I've regarded TP as the turning point. It's just a bit of shorthand here, so turning point. And SPOI, this is a long one over here. This is the stationary point of inflection. Okay. So if you're not quite sure what the stationary point of inflection is, then I'll probably suggest going back to revising cubics a little bit. Perhaps go back to the notes on cubics, or even cortex for that matter, and it will give you a brief idea on what it's about. But this is where, if you have a point of inflection, think of it as if you're traveling on a line that you can be turning to the right, and if you're on the path of this line, the stationary point of inflection is where you start turning the other way. So after that, you actually start turning to the left. This part over here, where you switch your direction, is your point of inflection. Now, if it's stationary as well, this implies that your gradient here is 0. Or you can say that f dash is equal to 0, where you have your stationary point of inflection. So, in fact, over here, a little bit of a mistake. I should really just say that the point of inflection, whether it's stationary or not, means that you have a turning point on your gradient function f dash of x. So we'll go through a few examples here just to demonstrate how we can use these rules to help us draw the gradient graph. If we scroll down over here to our first example. Now, we're shown here that f of x is quadratic of some sort. Now over here, we have some sort of quadratic. Is this positive or negative? Well, it's a smiley shape kind of quadratic, so we're going to say this is a positive quadratic. Now, if you have a positive quadratic and you take the derivative, then this must mean that f dash is a positive linear. Okay, so that's one clue. But other than that, I would actually suggest to look at the turning point on your original function. So over here, what we're going to be doing is we're going to be tracing down. So over here, I'll just scroll down. We're going to be tracing down from one graph to another. So when you're drawing a derivative function, it's nice to actually have it right below and have your x-axis parallel to each other. Well, parallel and have and be aligned. So where x is equal to 1, for instance, you want this to have a vertical line where you also have x equals to 1 over here. Now, we know that from above in our rule that if you have a turning point on f of x, then this must mean that you have a turning point. So we're referring to this one over here. So turning point on f, we have f dash equal to 0. So what we're going to do is we're just going to mark this and say that we have an x-intercept over here. And we know it's a positive linear graph. So we're simply just going to draw a straight line through this x-intercept and say that this is what our gradient function can look like. It's going to be a straight line, positive straight line that passes through an x-intercept precisely where you have an x-coordinate that has a turning point on your original function. Okay, so for this one down here, we have a cubic of some sort because it's actually given to us. Now, what kind of cubic? You know it's a negative cubic because we are starting from the top left and we end in the bottom left. So we're going to say we have a negative cubic. So this gives us a bit of information about f dash. We know it's a negative quadratic here. So we're going to end up with some sort of upside down parabola. Now remember, this just gives us an idea of what we can draw. What you do want to do is actually trace down all the turning points that you can see. Let's see one over here. So we're going to have a x-intercept on our gradient function because we know that f dash is equal to 0 when you have a turning point. And it seems like we have one around here as well. I'm just going to trace down. Okay, so if you have 2 points and you know that it's going to be an upside down parabola, you can now actually begin sketching. So upside down, passing through these 2 points. Okay, just redo that. I've seen better parabolas in my life, but it'll look something like this. Okay, so you may be wondering, but this turning point could be here or here. Does it really matter? Well, I mean, if you're not given enough values to actually determine the coordinate, and if you're not given this specific rule, then it actually doesn't matter too much. All we're looking for is the general shape. So this is actually quite okay. Now, in terms of what this turning point means, let's just have a look back at one of our rules. So right at the top, remember that if you have a turning point on f dash, so when I can draw a straight line, this one over here, it means that we have a SPOI on our, or not SPOI, a point of inflection on our original function. So this must mean that if you trace this back up, so just get my purple out, go vertically way back up, then this actually corresponds to a point of inflection on our original graph. Now, of course, the question doesn't actually request us to point this out, but it does become useful and provides us a bit of insight on why we can use derivative functions to actually not just draw them for the sake of it, but it actually gives us a lot of information about our original graph f. Okay, so one more down here. Okay, so over here, this is where we actually have a SPOI, not just the points of inflection. So we know that there's a SPOI at 2, 1. So just over here, this is a SPOI. Oops. Okay. Okay, so if it's SPOI, it's both stationary. If it's stationary, it also means that on your derivative function that you're going to have, well, let's just list it out over here. So for a SPOI, f dash is equal to 0, because we know that if it's stationary, that you're going to have a gradient of 0. So let's just underline that. So if we have this stationary part refers to this part over here, and the points of inflection part means what? It means that there's a turning point at this particular point as well. So this part over here means that there's a TP on f dash of x, also at this particular x coordinate. Okay, so we'll do a bit of tracing down here. So let's get the purple out. So when you want to trace down, you can see that there should be some sort of information down here on f of x. Since it's a SPOI, our gradient is 0, so that's why we got x-intercept directly below our SPOI. And you can see that the entire gradient is positive. Now, if this is the case, and we're not given it's a cubic function, but it actually doesn't really matter too much. If this is a cubic or quintic, it doesn't really matter, because if this is a cubic, you're going to end up with a positive quadratic shape. If this is a quintic with just one stationary point of inflection, you still have a quartic, but it's just a steeper parabola, so it doesn't actually matter too much here. But for the sake of simplicity, let's just say this is a cubic for now. So this is a cubic. But if you want to get technical about it, of course, as I said before, this can actually be any odd function, not odd function, a polynomial with an odd degree. So it can be a quintic, a septic, so a power of 7, or even a power of 9, doesn't really matter. So over here, if we're going to draw a positive parabola, because we know that this can look like a quadratic if we have, or if we assume that the green graph is a cubic, then what we're going to do is we're just going to draw a parabola. We have a turning point at that x-intercept as well, because we know that this must be a turning point due to this factor over here, where there's a turning point also where it hits the x-axis. So that's about it, really, and yeah, I hope this helps.